Hello there. We're on to our last experiment of the quarter, determining the nitrite concentration in seawater using UV visible spectrophotometry. Now, this experiment is very similar to the previous one where we determined the phosphate concentration. So I'm not going to go into too much detail about that procedure again because you already heard it all from me. Just going to go over the main differences in this experiment compared to the phosphate one. So in the phosphate experiment, remember phosphate is colorless in solution, but we needed to convert it into a form that had color, or in other words, absorbed in the UV visible range, because otherwise we couldn't use this method. So for that experiment, we formed a coordination complex. In this experiment, instead we're forming a colored compound due to the fact that it has conjugated double bonds. Okay. Oops. Okay, so the reaction that we do in this experiment is called the grease reaction. And let's go through that here. We're going to start with our nitrite. Okay, and we're going to react that with sulfanilamide, which looks like this. And oops, H2NS, 2-benzene, and H2. Okay, sulfanilamide. Okay, and that's going to react to form a diazonium ion. Keep doing this. Okay, diazonium. Okay, and the next step is to take that product, that diazonium atom, and we're going to react it with NED, which is just abbreviation for a very long organic chemistry name. NH, boop, 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 NH2. Okay, this is NED. And the product of that is going to be this compound that has lots of conjugated bonds and will be pink, meaning it absorbs in the UV visible. Oh, sorry. Okay, this product is an azo dye. It's called a dye because it is colored pink. One other thing to keep in mind in this procedure that's slightly different than the last one was that this is now a two-step reaction. So you need to make sure that you allow the first step of the reaction to go to completion before you add the second reactant, the NED. So when you do your time determination, keep that in mind. Since the rest of the procedure for the nitrite experiment is the same as the phosphate one, I'm not going to talk about that a whole lot more. The only thing that's really different with this experiment is part of your analysis needs to be about the limit of detection and limit of linearity of this instrument. So I'm going to just give a little bit of a lecture on what that means. I'm going to draw two graphs. Okay, one is going to be a calibration curve, the bottom one. You should all be familiar with this, where you have all of your standards and you plot their known concentrations against their absorbance, for example, in this experiment, or whatever signal you're detecting. This top graph is going to show what the instrument is actually seeing. So for example, let's say we run a blank. We put plain DI water into our instrument. What is it reading? Remember, on a UV visible spectrophotometer, the detector is a photomultiplier tube, so it's constantly being hit by photons and having some detection reading. So say, for example, we run a blank through and it reads something like this. Okay, there's a little bit of noise there always. And that blank might have some reading higher than 0 because you haven't zeroed your instrument yet. And so I'm gonna call that B, because it's going to correspond to the y-intercept on our calibration curve later. Okay, so B for y-intercept. Notice that this noise, the signal from this blank, has some noise given by the standard deviation, so that red line represents the mean of all of this data, but there's also a standard deviation associated with it, right? Sigma blank. Okay, now imagine then you put a very dilute sample into your instrument and you start getting a signal. So I'm going to erase right about there. And say your signal looks something like this. You start getting a little bit of a peak in there. Now, is that peak big enough in comparison to the noise for you to say that your instrument was able to detect it? So the definition of limit of detection is when that peak is 3 times larger than the standard deviation of the noise of your blank. Okay, so if this distance, which here I've drawn as the distance between these two line markings, is the standard deviation of the noise, that means our peak must be 3 times that. So it really needs to be 1, 2, 3. It needs to be all the way up here for it to be detected. So this peak is too small. Maybe our instrument does spit out some number, but we can't actually use that value reliably. But then, say we come along and we get a signal that's that big, that is 3 times larger. Okay. Now, also, if you do a calibration curve, that is something to take into account too. So when you ran your blank, where does that land on your calibration curve? On the y-axis. You haven't added any standard solution to your solution yet, and so it's on the y-axis and you get some reading B. Okay, that y-intercept on this plot. And then you have your series of standards. Maybe you get data points that look something like this, and you draw a trend line between them. Now, where is the limit of detection on a calibration curve? It's the same concept where we need the limit of detection to correspond to a signal reading that's 3 times larger than the standard deviation of the blank. In other words, we need a y value that is that y-intercept, that B, plus 3 sigma blanks. Okay. So in this example, it lands all the way over here, LOD. And let's walk through some math related to this. Okay, so this trend line looks like y equals mx plus b. Let's solve that for x. We want that x value corresponding to the limit of detection. Okay, when you solve it for x, it looks like that. Now, if the x value of the LOD is here, that means our y value for the LOD is here. Again, we need to be 3 times the standard deviation higher than what our blank mean is. So we can go ahead and plug in this value for the y value for the limit of detection. A equals b plus 3 sigma blank minus b divided by m. And now notice we have b minus b, so those cancel out, which leaves us with the formula that the limit of detection is equal to 3 times sigma blank divided by the slope. Okay, so that value represents the smallest concentration at which your instrument can detect a signal reliably. But being able to detect something is different from being able to quantify it. Okay, the limit of quantification is the same formula, but it's multiplied by 10 instead of 3. Okay, so those are always the beginning spot points on your limit of linearity, which is essentially just saying where is your instrument response staying linear on your calibration curve. Okay, so those are some things to keep in mind. Best of luck in expanding on this phosphate experiment now into our nitrite experiment. Okay, it's been a good quarter, and thanks for working with us.